Hello, Calculus 1 student. This is the lecture for section 2.6, which is all about related rates. And related rates are exactly what they sound like. They are rates that are related to each other. And generally, the idea with these related rates problems is that we use like a known rate in order to find an unknown rate. That's generally the idea. And related rates are really an application of implicit differentiation. So we can, so this is really gonna just be more practice of like section 2.5. It's just within, like here we're given some context. So we're gonna be looking at some application problems. So best way to do these or to learn how to do these is to just jump right in. So we're going to go straight to, I was thinking we could look at problem number 3 first. That's kind of one of the less complicated problems in this section. There are 9 problems. And then we'll look at either 8 or 5. I'm not sure which one yet. We'll see. After we do number 3, I'll make a decision. So you know what? I'll make a decision now. Well, let's do number 8. Yeah, we'll do number 8. So we'll do numbers 3 and 8 right now, and then if you have questions about any others, come to our work session, and hopefully I'll get to your question. If I don't during the work session, I'll always make a video later. So yeah, let's look at number 3. So number 3, it says that the altitude of a triangle is increasing at a rate of 2 centimeters per minute, while the area of the triangle is increasing at a rate of 3.5 square centimeters per minute. And then it says, at what rate is the base of the triangle changing when the altitude is 11 centimeters and the area is 85 square centimeters? So just in general, so I'm gonna write out steps that you can follow for solving all of these related rates problems. Follow these steps, you will be good. All of these problems can kind of be done in like 4 steps. You don't have to follow these steps exactly as I'm writing, because you know people do things in different orders, but this is, if you do follow these steps, you can get through all the problems. So let's see. So for the first step, what I recommend doing, and I recommend doing this for any type of application problem, like any type of word problem, identify your variables and give them a name. And when I say variables here, that means the same thing as when we say variables otherwise. You know, like you're using letters to represent numbers. But in this case, I specifically want you to just like be really, really, really cognizant of the fact that what you identify as variables, these are going to be values that are changing within within this situation. Think of the word variable. It has the verb to vary in it, V-A-R-Y. If I say something varies, I mean it changes. So when I say identify your variables, identify your values that are changing. Sorry. So yeah. And give them a name. So we'll identify our variables and we'll name them. So notice I have the altitude of a triangle. So that's one of my variables. Let's just call that H for height, because altitude is the same thing as height. So H will be my altitude. What else? I'm just looking for my variables. So the altitude of the triangle is increasing at a rate of 2 centimeters per minute, while the area of the triangle is increasing. So this is how we know these values are changing, right? So the altitude is increasing, they tell us. So I'm calling that H for height. I'm not, you can call it A if you want. I just decided to call it H for height because I know I'm going to be using the formula for area in a minute. Area of a triangle, which is 1/2 base times height. So that's why I called it H. So notice the next thing they also tell us is that the area of the triangle is changing, which makes sense. If the height is changing, the area is going to be changing, right? So it says the area of this triangle is changing, it's increasing also. And so let's call the area, let's just call it big A, just like normal whenever we're talking about like the area of a triangle, we say A equals 1/2 base times height, right? So we're going to call A the area. And then what else? It says, okay, the area is increasing at this rate. We'll get to the rates in a little bit. And then it says at what rate is the base of the triangle changing? Okay. So that's another value that's changing, the base. The base of the triangle is also changing. So let's just call the base B. So for base, B for base. So B is my base. Okay. So that's what I recommend you do for your first step. And once you've done that, my recommendation is that you write an equation that relates your variables. To each other. So just like any equation that you can think of that would relate your variables to each other, that's a true equation, write that. We'll get into the rate stuff again in a minute, but just looking at like height, area, base, like I know that an equation that relates all of those to each other is the formula for the area of a triangle, which is area A equals 1/2 base times height. So write an equation that relates your variables to each other. You'll notice in this section that this section takes you back to every formula you learned in geometry, every little formula. But I should say that one nice thing is that they do, like, notice for problem number 2, they do like actually write the formula that you're going to use there, which is very nice. Number 1, they don't write the formula, but it says area of a circle. So you want to think, okay, pi r squared, you know, stuff like that. So some of the problems, even though like you're dealing with these maybe formulas that you haven't used in a while or maybe never used, some of these problems, they do write the formula for you. So, and then others, you kind of have to figure it out. So this one I just, I'm thinking I have my height, I have my area, I have base, and I know an equation that relates those three. Area equals 1/2 base times height. So, so that's your second step. I'm gonna write down what we have so far, and then we're gonna go, I'm gonna switch over to the iPad. All right, I just wrote what we have so far, and I just want to reiterate that this right here, this was the formula for the area of a triangle. So that's how I got that Again, in some cases, they write the formula for you. In some cases, you have to like figure it out. In some cases, they give you a bunch of information and you can like get that information together and from that write a formula or write an equation. But in this case, I saw right away, okay, area of a triangle has base and height in it. And so I'm able to relate all my variables using that formula. So that's how I write my equation. Once you've done all this, what you're gonna do, and this is where the implicit differentiation comes in, is you're going to differentiate both sides of your equation. And here, so here's just something to be really aware of, that you're actually going to be differentiating implicitly. So this is section 2.5 that we're basically doing all over again, but just within situations where our variables represent something. So I wrote differentiating and I meant to just write differentiate. So you're going to differentiate implicitly. Here's where to be like extra careful when you're working with these related rates examples. Your variables, they are changing, right? Like that's how I decided what my variables were, like these values that are changing. And with all of these problems, your variables are going to be changing with respect to time, right? I guess this triangle is growing. And so the height is growing, the base is changing, the area is also growing. If the height is changing and the area is changing, if the height is changing and and the area is changing, that's what I meant to say, then your base is also changing, right? Or it's asking us how much is our base changing. And so all these three things are changing. You can imagine like a triangle expanding, everything's changing, and it's asking us how much is the base changing. But all of them, the area, the base, and the height, they're all changing with respect to time. Like the area, let's see, we go back to this. Like notice, notice with the problem, it says the area, for example, is increasing at a rate of 3.5 square centimeters per what? Per minute. Notice also, it says the altitude of this triangle is increasing at a rate of 2 centimeters per what? Per minute. And then the idea is that the base is also changing at some rate, but we're trying to find out what that rate is. But they're all changing with respect to time. It's always some number of centimeters or some number of square centimeters per minute. And so because they are all changing with respect to time, we can think of them all as functions of time. So I'm just going to go back to going back to to our variables, or to this instruction, or this step 3 in the instructions. I just want to like make a little note in a red color, so it's very, so that you can see it really well. I'm having a hard time finding words. But yeah, I just want to just make note of the fact that all of our variables are changing with respect to time, which means they're functions of time. So you might remember that that in the last section 2.5, when I differentiated implicitly, like anytime I differentiated something involving y, I had to multiply by y prime. We're gonna have to do this with all of our variables. So I just paused so I could find the notes from section 2.5. I just wanted to pull those up again. Just to remind you that with implicit differentiation, like what I have kind of circled right here, that whenever you differentiated an expression that involved y, you had to multiply by y prime because of the chain rule. You're going to be doing that for all of the variables in this case. So let's go back to the problem we were working on. So you're going to be using the chain rule for all of the variables. Since they're functions of time. So here's what I mean. We're going to differentiate this equation that we had. A equals 1/2 base times height. And so I'm going to say that so I'm differentiating the left side. That's not a huge deal. A prime equals, but then the right side of my equation, I'm going to, first of all, recognize that I have a product. And so let's just think of this as my F. And then we'll think of H as my G. And so I'm going to apply the product rule, which again says, I'll just write it here, that the derivative of F times G is F prime G plus FG prime. And so I'm going to just think of my, again, 1/2 B as my F. And here's where it gets strange. When I find my F prime, I will have 1/2, right? But then because B is a function of time, it's not just a B. So it's by itself. It's not just B independently. It depends on time. And so this is going to be 1/2 B prime. Some people write dB dt, just like I was saying in section 2.5, that some people write dy dx instead of y prime. Some people write dB dt instead of b prime. I like to write b prime because that's less writing, and I like to write y prime instead of dy dx because that's less writing. But some people do like to put that dt down there just to remind ourselves that we're dealing with function of time. So So you can either write 1/2 b prime or 1/2 db dt. Just make sure that you do have that b prime. It's not like if I had something like, if I were finding like the derivative of 1/2 x, I would just say this is 1/2, right? Constant times x, my derivative is just a constant. In this case, I can't do that because b is some function of time. And so because of that, it's like that b is like its own y. And so just like with implicit differentiation, anytime we differentiate something involving y, we multiply by y prime. Same thing with this here. So, so my f, if I think of my f in the product rule as the 1/2 b, then my f prime will be 1/2 b prime. And then if I think of my g in the product rule as my h, then my g prime will be h prime. Oops. So my g prime equals h prime. So given that all of that, I'm gonna now apply the product rule. So the product rule says first you take your f prime, which is 1/2. I'm gonna give myself some more room. So I will have my 1/2 b prime, that's my f prime, and then that's multiplied by my g, which in this case is the h, and then this is plus my f, which is the 1/2 b, and then times my g prime, which is h prime. So I end up with, well, that's all I end up with, huh? That's it. So that's actually the third step, is to differentiate both sides of your equation and make sure that you use the chain rule for all of your variables, including even that big A right there. It's not as clear, but A, I'm also using the chain rule with that. I'm also thinking of A as a function of time. Because, you know, normally if I were going to find like the derivative of just x, I would just say that's 1, right? But over here, when I find the derivative of A, I'm thinking 1 and then A prime, although I don't write the 1, right? I just have my A prime. So, but that's really what's going on there. It's still that chain movement happening. And so I'm still like doing the same implicit differentiation thing where I multiply each variable by its derivative with respect to whatever. In this case, it's with respect to time. So now we're going to do the last step, which is to, so you might have noticed I skipped over a bunch of stuff when I was reading through the problem. So now we're going to go back to the stuff that I skipped over. And basically, we're going to plug in the given values and known values, like sometimes the value, like in this case, I think all of the values are given to us, but sometimes like a value, even though it's not given to us, we can find out what it is. So we'll plug in the given values and then solve for the value that we're trying to find. And I should just say that that value is usually going to, I mean, not usually, in all of these problems, that value is going to be a rate. So I'm just going to write rate there. So I'm gonna go back to the problem and let's see what these values are that we're given. So the first thing is that we're told that the altitude of this triangle is increasing at a rate of 2 centimeters per minute. So this is telling us that the rate of the altitude is, or the rate that the altitude is increasing is 2 centimeters per minute. And here you want to keep in mind that rate is the same thing as derivative. So derivative is instantaneous. Trying to spell that. Did I spell that correctly? And I did not spell that correctly. Yes, there, instantaneous rate of change. So that's derivative. So when you see rate, then you want to think, okay, that I'm dealing with derivative here. And in this case, this is the rate of the altitude. So the altitude was h, right? That was the height. And so rate is the derivative of the height. And we're told that that equals 2. Next, we're given that the area is increasing at a rate of 3.5 square centimeters per minute. So area I referred to as big A. And its rate, we're told, is 3.5 square centimeters. So again, rate is the same thing as derivative. So I can say A prime equals 3.5. We're being asked at what rate is the base of this triangle changing? So in this case, we're trying to find, this is asking us to find the base's rate, right? Which means we're trying to find B prime. That's our job. Let's see, they give us a couple of other numbers. They tell us, what else do they tell us? They tell us that they want to know the rate that the base is changing when the altitude is 11. So they're saying at this moment, we're going to find out when the base is changing at the moment when the altitude, when h is equal to 11. H was what I called the altitude. And then the area is 85 square centimeters. So one other piece of information we are given here is that the area of this triangle is 85 square centimeters. This is at the moment that we want to find the rate of the base, the rate that the base is changing. So big A is 85. So those are like, we're given a bunch of known values, we're given a bunch of values. And we're gonna plug those in. I'm just gonna write these on my iPad. We're gonna go ahead and plug them in. All right, I wrote everything down, like all the information that we had from that page. And I'm looking at the, like what we have, or like what we're given, or not what we're given, what we found in the third step, right? I got this equation in the third step. And I know that I'm trying to find out what B prime is. That's what I'm trying to find. And notice the equation, like after I differentiated implicitly, notice the equation, it has an A prime. The equation also has an H in it. It also has an H prime, and it also has a B in it. Like, notice this B. So basically, like, I have a bunch of given values, and basically values for everything, but I don't have a B. And I'm trying to find B prime, and so I want to have only one unknown in that equation, and right now I have two unknowns. So like, notice if I go and I plug everything, if I take this equation that I had, right, and I plug in my given values, look at what I get. I have 3.5 right here for my A prime, right? And then the B prime, that's what I'm trying to find. I have the H is 11. I don't know what B is. And then I have the H prime is 2. So I need to find out what the B is before I can find out what the B prime is, right? Because I have too many unknowns here. So my job is to find B prime. And I was thinking they gave us all the values that we needed, but it looks like they did not. But they do give us the information that they do give us enough information for us to find this other value, this B. And what I'm going to do in order to find B is I'm going to use the very first equation that I wrote earlier. This one, A equals 1/2 times B times H, that formula for the area of a triangle. I'm just going to go ahead and use that along with, so this is all, like, what I'm about to do right now. I'm just going to find B. Here, I'm going to do this off to the side over here. Finding B. And again, I'm going to be using this area of a triangle formula, A equals 1/2 base times height. And I'll use like what they give us, that the area at this moment is 85. And then I don't know what B is, but they do give us that the height is 11. So using that, I can find out what my B is, right? So what I'll do to find B is I'll let's just multiply both sides by 2 to get rid of the fraction. I'll multiply both sides by 2. 2 times 2 over here times 2 over here, although it's hard to see. And over here, the 2's cancel. That's on the right side, the 2's cancel. And then on the left side, let's see, 2 times 85. I'm tired. The math, I think it's 170. Is it 170? I think it is. And then equals B times 11. And then from here, I can get B by itself by dividing both sides by 11. Right. Over 11 over 11. If I did the math correctly, my B is 170 over 11. And so now I can go plug that in. So I'm gonna take this and plug it in right here. Let me just erase this B and replace it with 170 over 11. 170 over 11. There. Okay, now, yay! I have B prime as the only unknown here, and now I can solve this equation for B prime. So, so notice I guess it looks like I can cancel these 2's out, right? Over there. So what I have is 3.5 equals 11 over 2 B prime plus that's just 170 over 11. And so now I will, again, I'm working to solve for B prime. I'm just there. So I'm working to solve for B prime. So I'm gonna move that 170 over 11 to the other side of the equation. So I'll subtract that from both sides. Minus 170 over 11 equals 11 over 2b prime. And then from there, I need to get b prime by itself. So I'll multiply both sides by 2 over 11, or divide both sides by 11 over 2, which division is the same thing as multiplying by the reciprocal, which is why I'm going to go ahead and multiply both sides by 2 over 11. And this is like so ugly and messy, but you know what? I don't care. I don't care. You know why? Because I'm just going to use the calculator. That's what I'm going to do. And let's see what the calculator tells us. Let's see. So I have 2 over 11 times 3.5 minus 170 over 11. What a mess, huh? My goodness. Oh, wow. Wow, does that make sense? That the area is increasing at this rate, and then okay, so here, notice what the answer is. The answer is approximately negative 2.17. I'm just writing that down. And the reason I like gasped, here's why I gasped. It's not that big a deal, but notice the answer is negative, right? Whenever you have a negative answer for a rate, like if you have a negative rate, that means that the negative rate means the whatever you're talking about, it's decreasing. So in this case, that means that the base is decreasing. So while the height of this triangle, it's increasing, and the area is also increasing by a certain amount, but the base is decreasing. So let's see if this is correct. So the base is decreasing, and I just assumed that the base would be increasing because I was like, well, the area is increasing, but I guess it doesn't have to be. If the you have a triangle and the height's increasing, if the height's increasing enough, even though the base is decreasing, the area can still be increasing, right? So let's check this out. It was negative 2 point, I don't know how many decimal places they want. Let's just do this many. And I guess they took this, but let's check to see how many. Oh, they put in all these numbers, which don't even show up on our calculator. So, but they accept this, so we're okay. So, so yeah, it looks like the base is decreasing, even though the area is increasing. So that's possible, right? As long as the height is increasing enough, the base can still be decreasing, and base times height can still end up being, base times height can still end up increasing. And therefore 1/2 base times height can still end up increasing. I think I said I was going to do number 8 next, so let's do number 8, and then if you have questions about the others, we'll go over them. Let's see. I'm going to get rid of this stuff and then go on to number 8. So number 8, it says 2 cars are moving towards an intersection. One car is 170 meters north of the intersection and moving towards the intersection at 20 meters per second, while the other is 180 meters west of the intersection and moving towards the intersection at 14 meters per second. And the question is, how rapidly are the cars approaching each other 3 seconds later? Okay, I'm gonna draw a picture for this one because it's hard for me to picture it without a picture. So I'm gonna go ahead and draw a picture. So for the first step where I say, like, you know, identify your variables, give them a name, I'm gonna draw a picture to do that in this case. Okay, so let's say that the intersection is, right. Okay, let's say that this is the intersection, okay? That little black box that I just drew. And let's draw the first car. So this is the first car. One car is moving. One car is 170 meters north of the intersection and moving towards the intersection at 20 meters per second. So it's north of the intersection and there it's moving towards it, right? So let's just refer to the distance of this car as the one that starts off north and moves towards the intersection. Let's refer to the distance of this car as let's just call it B. It shouldn't be that hard for me to think of the letter, but it was because I'm tired. So let's just call this B, okay? And then let's see what's happening next. So the other, and by the way, I'm kind of not paying attention to these numbers just yet. I'm just naming my unknown values, or sorry, my variables, my values that are changing. You know what? I should draw, you know what, that's not a great picture. I'm gonna draw something that's better because I just said I'm not paying attention to the numbers, and I just noticed I should pay attention to this number, this 170, when I'm identifying my values that are changing, my variables. And that's because this car, it starts off 170 meters north, right? So it starts off like this far from the intersection. So like this entire distance right here that I just wrote is that distance, like where it starts, that doesn't change. That whole distance is 170. Okay. Like this is its starting point that I'm marking right now. And that distance from there to the intersection is 170 meters. And now I'll still name its distance, the distance that this car travels, I'll still name it B, but I just want to point out that that it started off being 170 meters from the intersection. So that's going to help us it looks like. That'll help us set up our equation in a moment. But I'm just gonna call B. I'm gonna call the distance that this car has traveled B. And let's look at the other one. The other car says is 180 meters west of the intersection. So let's say it's something like this. I'll try to draw that a bit more horizontal. And that is 180 meters west of the intersection. So its starting point is 180 meters from the intersection. But I can define a variable, as in this is a value that's changing, right? And this car, it says it's moving towards the intersection also at 14 miles or meters per second. Let's call the distance that this car moves, let's refer to it as A. So, and then let's see, the question is, how rapidly are the cars approaching each other 3 seconds later? So we're trying to find out how rapidly these two cars are approaching each other. So we're trying to find out the rate of the distance between the two of them, right? Like as they get closer and closer to the intersection, their distance is decreasing. And so we're trying to find out how quickly that distance is decreasing. So that green line I drew, we're trying to find out that rate. And I'm just going to refer to that as C. And notice what I've drawn is a right triangle. And so, so my first step, I know that was a long time doing that. That took a while to do that first step. My first step, just identifying my variables, took some time. Oftentimes that's the hardest part, because once you have that, then notice, look, I just see it right away. I see, oh, I have a right triangle. So that tells me for my second step where I need to write an equation that relates my variables to each other, I'm going to use the Pythagorean theorem. One thing is I'm going to use this triangle here that has like the blue line segment, the red or the blue base, the red height, and then the green hypotenuse. But I need to before I go to my iPad and draw this triangle, I need to do something. And this is what I need to do. I need to just say that the base of my triangle is 100 minus A, because this car was a distance of 180 meters total from the intersection. And then it drove A meters. And so now it's 180 minus A. For example, let's say I start off 180 meters away, and then I drive 10 meters, or let's say I drive 10 meters. Now I'm just 170 meters away. Or if I started off 180 meters away and I drive 20 meters, now I'm just 160 meters away. So I'm getting those numbers by subtracting 180 minus the number of meters that I've driven. So that's how I get this 180 minus A. And I'll do the same thing for the B, for the height of my triangle. Like I started off 170 meters away, but I drove B meters. So now I'm 170 minus B meters away. So now I'm gonna just draw this triangle on my iPad and switch over to my iPad to do the second step. problem. So here's my triangle that I got from the screen. And now I'm gonna just put all the pieces together, as in I'm going to write an equation that relates my variables to each other. And I'm just noticing that this is a right triangle, so I'm gonna use the Pythagorean theorem. Oh, okay, maybe the triangle I drew is not a right triangle, but you get the idea. It should be a right triangle. Okay, I'm not gonna redraw it, but you get the idea. Right triangle, right? And I'm gonna use the Pythagorean theorem. So just a reminder that if you do have a right triangle, and this is A, B, C, the Pythagorean theorem says A squared plus B squared equals C squared. So I'm gonna go ahead and use that. And so in this case, I'll have 180 minus A quantity squared plus 170 minus B quantity squared equals C squared. And now third step is to use my implicit differentiation. So I'm gonna differentiate both sides of the equation using implicit differentiation, remembering that A, B, and C are all functions of time. So I'm always gonna multiply by A prime, B prime, C prime when I differentiate involving those variables. So, so first of all, I'm gonna use my power rule. So bring that 2 down. And one thing to remember is that while I did just use the power rule, I used it on a function that was more than just x. My function was 180 minus A. And so I have to use the chain rule, which means I have to multiply by the derivative of what's inside these parentheses here. The derivative of 180 is just 0. But the derivative of minus A is negative 1A prime. That's what I was talking about whenever you differentiate something involving A, B, or C, like your variables in this case, they're functions of time. So you want to multiply by A prime or B prime or C prime. For the next one, I will have 170 minus B raised to the first power, but because I have more than, because I have more than, what is that? More than just X that I was using the power rule on, I have to multiply by the derivative of what was inside these parentheses. Derivative of 170, no problem, that's just 0. But B, when I find the derivative of that, I'll get negative 1B prime, because B is a function of time. So I'm multiplying by the derivative of that. And then last of all, once again, power rule. So I have 2C, but then because C is more than just an X, C is a function of time, I have to multiply this by the derivative of C, or in other words, C prime, or some people will write dC dt. Some people will write this. And some people for the B prime will write dB dt. And some people for the A prime will write dA dt. I just like to write A prime, B prime, C prime, less writing. But there is an advantage to writing the dA dt, dB dt, dC dt, and that's a reminder that you're dealing with a function of time. And then if you do take calculus 3, which is calculus with more than, it's called multivariable calculus. And so sometimes you're not always differentiating with respect to like the same variable. And so it's helpful to know what you're differentiating with respect to. So that's an advantage to writing all this. Okay, so I just did the third step, and now I'll go ahead and do the fourth step, which is to plug in values that are given and then like values that we can find. So I'm going to go back to the problem and let's see what's given to us. So it says the first car whose distance I referred to as B, that car, it says, what does it say about that car? It says that it is moving 20 miles, I keep saying miles, meters per second. Meters per second. And so what that tells me, I'm sorry, everybody. Sorry for yawning. Oh my gosh, I'm tired. It's kind of, yeah, I'm just tired. So B prime is equal to 20. Because B was my first car's distance, right? And again, rate is the derivative. So in this case, we're talking about distance over time, which means we're talking about velocity. So velocity is derivative. What next? The other car, which I referred to as, I've referred to its distance as A. And that one, it says that it is moving 14 meters per second. So I can say that my A prime is equal to 14. They don't give us that much info, do they? But they do tell us that the cars have traveled for 3 seconds. So it says, how rapidly are the cars approaching each other? 3 seconds later. So this is telling us that they've traveled 3 seconds, which I guess will give us enough information to find the other values that we need to find. So I'm going to go ahead and write this information on the iPad, switch over. Actually, I'm not going to switch over just yet, because I just want to say that this part about traveled 3 seconds, that's giving us the ability to find B and A, basically to find the distance that these cars have traveled. And we're going to do that using the formula rate times time equals distance. So rate times time equals distance. This formula, I'm sure you've heard of, but even if you haven't like consciously heard of, you know the formula, because it's basically saying that the amount of time you drive times how fast you drive will give you your distance. So rate, that's how fast you drive, and then time is the amount of time you drive. So like if I drive 60 miles per hour for 2 hours, I will have driven 120 miles. Rate 60 times time 2 equals my distance, 120. That's right? So so yeah, we can use this formula to find B and to find A, because B represented the distance that the car that was north traveled. So I can say that my B is equal to its rate, which was 20, times the number of seconds that it's traveled. So 20 meters here, I'm just going to put in the units just to make it clear. 20 meters per second times 3 seconds, rate times time. And that gives us 60 meters. That's our B. We can do the same thing for A. A was traveling 14 meters per second for 3 seconds. and what's that, 42. So that's 42 meters that A has traveled. So I have my A now, I have my B, I have my A prime, and I have my B prime. And I think that's everything that I need, because I'm trying to find out, oh, it's still not everything I need. Oh, we'll go back to the problem. Look at me, look at me. This is just one problem and you all have 9. So who am I to complain, right? I'm gonna write this stuff and then we'll switch over to the iPad. So the reason I just made that sound of exasperation is that I was like, oh, we have everything that we need. We have our A, we have our A, we have our A prime, we have our B, we have our B prime, and then I was like, we don't have our C. And basically we're trying to find, our job right now is to find C prime, because it's asking us how, just going back to the problem, it's asking how rapidly are the cars approaching each other, which that, and the distance between the cars was the C. And so we're trying to find out how quickly that C is changing. Which means that, so this last sentence is basically telling us, find C prime. That's what we need to find. And I just like noticed we have everything that we need, right? That's in that equation, except for the C in order to find C prime. So, because like we're trying to, trying to solve for C prime, but we have more than one unknown now. So we need to find out what that C is. So we're going to go ahead and find the C. And again, just like in the previous problem, we can find the C in this by using the equation that we got, like in the second step here. This equation, we're going to use this to find C. So just make a little note. Right now, we're going to start finding C. Finding C. So we have 180. So I'm using the equation from step 2. This equation right here. So I have 180 minus my A, which was the 42. And this is quantity squared, plus 170 minus my B, which was 60, quantity squared equals my C squared, what I'm trying to find. And I'm just going to go straight to the calculator for this. So we have 180 minus 42 quantity squared plus 170 minus 60. I should have been able to do that right there. 170 minus 60. And then quantity squared. And I get 31,144. I'll write that down. So that's my C squared, 31,004. Did I write that down correctly? I'm gonna check to see if I wrote that down correctly. Okay, I wrote it down correctly. So my C squared is 31,144. And then to get C, I take the square root of both sides. And in this case, I actually don't have to put the, you know how usually you put plus or minus on the other side, because you can square a negative and still get a positive. This time I can ignore the minus one, because I know that C represents the the distance between these two cars, and so that distance, it can't be negative, so. My C will just be positive square root of 31,144, which I do not think is a perfect square, but let's just check to be sure. So if we take the square root of the answer, we do not get a perfect square. So I'm just gonna leave it in this form, square root of 31,144. I keep having to like stop when I read this because I'm like 2 1s and 2 4s. Okay, so I have my C now. So now I can plug all of like everything that I have into the third equation here. So this will be 2 times 180 minus my A, which was 42. And then times -1 times my A prime, which was 14. And then plus 2 times 170 minus my B, which was 60, times -1 times my B prime, which was 20. Oh, my goodness, I'm running out of room. Why didn't I write more small? Here, I'm gonna rewrite this, but in your world, it won't take long. Okay, I rewrote it smaller so that I could fit the 2C prime in there. That's a C prime. You can't see it, but see, that's a C prime. So I wrote it so I could fit that in there. And then now I'm pretty much done. I'm just gonna use a calculator. So, because my goal is to find out what C prime is. So I'm gonna divide both sides by this 2 root 31,144 in order to get C prime by itself. So I'll go ahead and do that. Divide both sides by 2 root 31,144. And I'm just gonna use calculator, like that's like what I'm gonna do. So all this cancels, and once again, let me just say, because I kind of wrote this out while I was paused with recording, I replaced the C. I replaced the C here with the square root of 31,144. So that's how I got the right side of that equation. And now dividing both sides by 2 root 31,144, let's see what we get. So I'm gonna enter just like the left side of this thing, I'm entering all of that in Desmos, the wonderful scientific calculator. So I believe I entered my numerator correctly, and then this is all over 2 root, well, I can just put answer root. Actually, you know what, let me just enter it like this. I want to clear what I'm entering. And that's what I get, negative 23.41386541. And that's going to be my answer. And once again, like for this problem, it looks like we have a negative negative answer, a negative rate. That's the word I was looking for. And negative rate just means that your value, whatever this value is, it's decreasing. In this case, the value that we're talking about is the distance between the cars, and it makes sense that the distance is decreasing because they're both going towards the same intersection. So their distance between each other is decreasing. So whenever you have a negative rate, that means your value is decreasing. If we had a positive rate, it would be increasing, but that wouldn't make sense because the cars are both going towards this intersection, right? So, so negative 23.414, let's just say. Oh, by the way, so it says the cars are getting closer together. And then I think they want us to just write the answer as a positive number, because I think they are asking us to like write the answer the way you would if you were talking to somebody in the real world who's not a mathematician or a physicist. So let's see. I'm actually not sure, but yeah, so they just wanted us to write the positive version, or like, you know, like if I were saying, oh, I was going 20, if I'm so okay, so if I like go from my house to Laney, right? Let's say I'm commuting and I go from my house to Laney, and I drive 60 miles per hour. My rate, I would say, is 60 miles per hour. But if I drive from Laney back to my house, the distance between me and my house is now decreasing. So going to Laney, my distance between me and my house is increasing, but then returning from Laney, the distance is decreasing. So going, math speak, I would say that my rate is positive 60 miles per hour. But returning, I would say my rate is negative 60 miles per hour, if we're talking about my distance as being the distance between me and my home, right? But if I were just speaking with a person who does not speak math, right, I would say, oh, I drove 60 miles per hour to go back home, right? So I think that's what they're asking for here. Like when they say, first of all, the cars are getting wet, closer together. So they want you to recognize that when you got a negative result here, that meant that their distance between each other was decreasing. And then at what, so they're asking you to speak just regular language, English language versus math language, right? If you were speaking math language, all you would have to do is say the rate of C is negative 23.414. And that would tell a math person who's reading it that the distance between those cars is decreasing. That would tell a math person the cars are getting closer together, right? But I guess they're asking you to write this in everyday language. So anyway, good luck with this homework. If you have questions, make sure you come to the work session and we'll go over as many as we can. As you see, these problems take time, and so I feel for you. But have fun with it. Have fun with it, knowing that you have all the tools that you need to do it, and also knowing that you can always ask me how to approach the problem. So take care. Bye.